Okay, good afternoon, everyone. So we're happy for today, for the Quantum Colloquium, to have Chandrasekhar Ramanathan from Dartmouth College, who's going to tell us about quieting noisy neighbors, extending the coherence times of central electronic spins in solids. Chandra, please.
Well, thank you very much for the introduction, for the invitation to give the colloquium. I must apologize for not being there with you today. I unfortunately was not able to travel this time. Hopefully can do it in the future. So today I want to tell you some of the work that we're doing on our studies in spin systems and extending coherence times. And for those of you who are not familiar with it, the title comes from a statement by Sir Alex Ferguson, who was who was a manager of Manchester United many years ago when Manchester City was just starting to raise its profile in football. But it is an interesting title because essentially the coherence of electronic spins in solids is typically limited by other spins in its neighborhood. And it's the fluctuations and the noise created by those surrounding electronic spins that influences the coherence time. And if you can suppress those fluctuations and suppress that noise, if you will, you can extend coherence times. Oops. Oh, give me a second. There we go. Okay, first of all, I wanted to acknowledge some of the people who've done the work so that it's not pushed to the end. Some of the work on silicon that I'm going to show you on donors in silicon was done by Li Huang Zhu, who's a graduate student of mine who's now at IQM in Finland. The work was taken over by Ethan Williams, who's another graduate student who is currently finishing up, who's also done the work that I'm going to show you in Diamond. And Hans van Tol is a scientist in charge of the High Field Magnet Lab EPR facility, which is where some of our experiments were done. And of course, our funding agencies. So again, this is a quantum colloquium, so I don't need to introduce quantum physics applications to you, but just again, to remind us why we're doing this, there are a lot of promising technological applications of quantum physics, and especially in the last 2 decades, there's been a lot of focus on quantum computing with a variety of different platforms. There's a dilution fridge shown here with a variety of superconducting circuits, quantum communication protocols where you have optical repeaters and switches, quantum simulators, which are, of course, now crossing over into quantum computing. There's some beautiful work on neutral atom arrays that are being used for quantum computing from Quera. And of course, there's an overlap there between quantum simulation and computing. And from a more widespread practical standpoint, quantum sensing has a lot of potential, whether it's using cold matter systems to study, underground mass changes for gravimeters, or looking at single molecules, for example. This is a Diamond NV work, which is probably the most closely related to what I'll be telling you about today. So there's a lot of potential here, some more near term, some for the longer term. Again, just to make sure we're all on the same side, we're all on the same page. Our qubit is a 2-level system, and it can be in a 0 state or 1 state. There are fiducial states of the system, which we encode information. There's an energy gap between the two. Delta E is given by h bar omega. Our favorite implementation of this qubit is a spin-half system. So our eigenstates of the system are to spin down and spin up. Again, the energy difference is h bar omega. The Hamiltonian of the system that for our spin-half particle in an external field is just the Zeeman Hamiltonian. So it's omega I SZ. And of course, the distinction between a bit, which is just a 2-level system, is that a bit can only be 0 and 1. And a qubit, of course, can be in a uniform superposition of 0 and 1. And so there are an infinite number of single qubit states that can be mapped to the surface of the Bloch sphere. So we have a continuum of possibilities. Just a definition of qubits. And of course, you all know that quantum states are fragile and can't be copied. So one of the key distinctive features why we don't have quantum computers is that this fragility is essentially the challenge, right? We want to maintain coherence, the ability to maintain a superposition. And for example, if you have large cat states, like this entangled state here, any slight disturbance is going to lead to a collapse of that state. And so this is our experimental challenge. I'm going to build something is, how do I protect these states? How do I extend coherence times? How do I protect not just, eventually we'll need to get to the point where we're not just protecting isolated single qubit states, but protecting highly correlated multi-qubit systems as well. All right, just to give you a sense of our the experiments I'm going to show you, I want to give you a very brief introduction to magnetic resonance, because that's the experimental platform we use in my lab to study the properties of these spins. So we put a spin, and what we typically do in these magnetic resonance experiments is we do ensemble measurements. So we have a sample placed on a large external magnetic field. It's a system of spins. The energy classically, of course, is just mu dot B. I've dropped the minus sign for convenience. And of course, I can convert that into a Hamiltonian, and I just get my right standard Zeeman Hamiltonian. And for now, I'm going to pretend to be a good theorist and set h bar equal to 1. And my Lamer frequency is just the gyromagnetic ratio times the strength of the external field. So since I have an ensemble of spins in the system, all of the spins are precessing here at exactly the same frequency, let's say for now. They're all at exactly omega naught. But the challenge is that they're all precessing with a slightly different phase. And so if I look at the bulk magnetization of the system, there's a net longitudinal magnetization along Z, because that's a preferred energy direction of the system. But there's no net transverse magnetization. So spins can be detected like this by just detecting the bulk magnetization, and that was done with what's called longitudinal detection. You could use things like squid magnetometers or atomic magnetometers to detect them. They're usually bulky systems and only used in limited cases. What we do typically in a magnetic resonance experiment is we do pulse magnetic resonance. We excite the spins and see how they respond. So if I think about applying a radio frequency field along the x-axis now, if I take my radio frequency field dx of t, I'm going to write it in the form 2b1 cosine omega t. It's an oscillating field. I can always rewrite that in terms of two components, just expanding the cosine, as b1 exponential e to the I omega t plus b1 exponential e to the minus I omega t. This can be thought of as two counter-rotating fields, right? Any oscillating field can be decomposed into two counter-rotating fields. One, which is in blue, is the counterclockwise component, and in the, I can't see the color here. The grayish color is the clockwise rotating component. Now, only one of those components is going to be rotating in the same sense as your external magnet, as your spins. And so what we do, we use what's called the rotating wave approximation. We ignore the component of the spins that's rotating in the opposite we ignore the component of the field, RF field, that's rotating in the opposite sense of the spins. So in that rotating frame of reference, that's rotating with the RF. Now, with the RF component that's in the correct direction, we can write an effective magnetic field, which is just the difference B naught minus omega over gamma along the Z direction plus B1x. And now on resonance, of course, B omega is equal to gamma B. That's if I'm applying my radio frequency fields on resonance, the component along Z goes to 0, and I just have a field along Z, along the X direction. And of course, now, since that's the only field present in the system, my magnetization or my spins are going to precess about the x-axis at a frequency omega equal to gamma b1. Of course, this is just a Rabi frequency. And so we rotate the spins until they're along the xy direction. So we apply what's called a 90-degree pulse, or pi over 2 pulse. The rotation time is for period time t is equal to pi over 2 omega 1. And magnetization rotates from the z-axis to the y-axis. So this is just the simplest gate that you can have. It's a 1-qubit gate. We rotate the spins onto the xy plane. And of course, at that point, we turn off the radio frequency field, and the spins will continue to precess in the xy plane now. And the RF coil is still present there in the xy plane. The RF coil sees a time-dependent magnetization of the form m cosine omega naught t, and of course, induces an EMF in the coil. It's given by omega naught m sine omega naught t. And that's our signal. That's what we call a free induction decay. That's what we measure in a bulk magnetic resonance experiment. Now, if I'm doing electron spin resonance, I'm at a higher frequency. I will change this RF coil into a cavity of some sort. It'll become a resonator rather than a lumped element circuit, but the idea is exactly the same. Okay, so this is the basic form of the experiment that we do. And you can start to see why this gives you why something like this can be used for magnetometry, right? My Larmor frequency is proportional to the strength of the magnetic fields. If I take my decaying free induction decay and do a Fourier transform, I get a spectral peak. And you can see that the location of this peak essentially identifies the strength of the magnetic field. The longer the coherence time, the narrower the peak, just from a Fourier uncertainty principle. And so by extending my coherence time, I'm going to improve the accuracy of my sensing, because I'm going to be able to resolve peaks more carefully. So that's one of the key features in quantum sensing, is I want to have a really long coherence time while also maintaining sensitivity to whatever field I'm looking at. And this often becomes a challenge, is how do you do both of those things? And just to give you a sense of what happens, in most physical systems, of course, the only way you get a uniform magnetic field is if you have an infinite solenoid. You don't get infinite solenoids in the world. So what I've shown at the bottom here are distributions of magnetic fields. So on the left is a narrow distribution of magnetic fields. On the right is a broad distribution of magnetic fields. And if I just see what happens to my FID as I add spins that are now seeing this narrow distribution of magnetic fields, you see that the free induction decay that was normally extending out all the way starts to decay much faster. And this is one of the primary causes of decay if a signal is the fact that you have a distribution of fields. There's a incoherent sum of unitaries, if you will. And so this is what happens when you have a narrow distribution. If you have a broad distribution, you can see that the decay is much faster. And of course, they're related by a Fourier transform, right? A broad distribution is going to give you a much faster decay. Now, this is a fixed decay. It's a distribution of fixed fields in the system. And what we want to do in most cases is find a way to overcome this. So that is our favorite experimental tool right now, is what's called the spin echo on the Hahn echo. So this is a set of animations from Wikipedia. It's a really nice animation, so I didn't remake it. It's from Gavin Morley. And so what you do is you apply a 90-degree pulse, you wait a time t, then you apply a 180-degree pulse, and after a similar time t, there's an echo. And you can visualize that process here. So the spin, that's 90. Now the spins dephase. The 180 flips all the spins, but as they continue to evolve, they rephase and form an echo. So that's the idea of what happens during a spin echo. It allows you to rephase the static distribution, refocus the static distribution. Now, what you can then do is by changing the time t, you can then actually measure the coherence decay. And that essentially is what we normally think of as a T2 of the spins. So by changing t, we can actually measure how the coherence is decay. And that gives us a measure of the lifetime. So we're removing the effect of this inhomogeneity, but what's left over is due to some intrinsic T2, potentially. Okay, so spin echoes are going to be a key component of what I'll be describing today. Okay, so let's move on to the two physical systems that we study in my lab. They're both solid-state spin systems. We study both defects in diamond and donors in silicon. So defect diamond is, of course, both diamond and silicon are from group 4 elements, carbon and silicon. In defects in diamond, we're looking primarily at two different electron spin systems. One is the nitrogen vacancy center, which most of you would probably heard of. It's where nitrogen is adjacent, a substitutional nitrogen is adjacent to a vacancy in the lattice. It's a spin 1 defect, and it ends up being a 3-level system. The beauty of the NV center is that it can be optically initialized and read out, which means you're able to do single spin detection, and you can still get pure states even at room temperature. The P1 center is just a substitutional nitrogen. There's no defect adjacent to it. It's a spin half defect. What's interesting about it is that it has very, very long coherence times. It's very similar coherence times to the NV center. And whenever you have NV centers, you have P1 centers. So the NV centers, the P1 centers often form a bath for the NV center, but they're also increasingly being used as a platform for quantum simulation themselves. Now, in the background of all of this, you also have carbon-13, which is present. It's a nucleus spin, which is present at 1.1% abundance in the lattice. So about 1% of all the carbon spins are carbon-13. And they're also processing, and they're also interacting with everything that you have. So that's what this figure on the left represents. Now, I should point out that when we deal with nucleus spins, we can ignore the orbital component, the spatial component of the spins. But with electronic spins, we really do have to worry about their orbital components. How does the wave function extend? With both the NV center and the P1 center, we have strongly localized electronic orbitals. So we're typically looking at the extent of the wave function extends less than a bond, or about or at the most of a bond length. So they're highly localized defects. When I come to something like a donor in silicon, though, the picture changes dramatically. Even though in some ways it's a very similar system, I'm going to take silicon and remove one substitute a phosphorus donor in the silicon lattice. But now, because the phosphorus donor in silicon is a shallow donor, and what you end up getting is that you have a highly delocalized electronic wave function, and so the Bohr radius here is on the order of 2 nanometers. So the electronic wave function overlaps many, many nucleus spins in the system. So here my donor electron is coupled to many nucleus spins. So the noisy neighbors are the silicon 29 nucleus spins, but when I'm looking at donors in silicon, and there's a lot of them. When I'm looking at defects in diamond, if I'm looking at an NV center, the neighbors are primarily the P1 centers. There are some carbon-13s as well that are important. When I'm looking at the P1 centers, it's usually other P1 centers as well as a carbon-13 that are the neighbors that we need to worry about that cause a decoherence. All right, so let's go a little bit further. Start to write a little bit of math in here. So I'm looking at my Hahn echo, and there's a pi/2 pulse, a decay, a delay, a pi pulse, and then an echo. So if I look at my offset delta I as being a local offset, if it's fixed, and then I look at the phase evolution, which is just gamma E delta I times T, the phase is going to grow constantly. The pi pulse flips the phase, and then the phase grows constantly until I refocus all my phases go back to 0 at the point of the echo, which is what the Hahn echo is doing. So essentially, irrespective of what the nature of this phase delta I is, the magnitude doesn't matter. That's what the Hahn echo does. You can have a distribution of these, but you'll have just the slopes of these will change, but they will all invert and all come back to 0 exactly at the height of the echo. And so the Hahn echo refocuses static interactions. So things like magnetic field inhomogeneities, like I mentioned earlier, or spin interactions with isolated, unlike electronic or nucleus spins. So things are not affected by the pulse, but essentially don't interact with anything else. They cause a fixed offset in the field. So anything that has this form where delta I is a constant is going to be refocused by the Hahn echo. However, if I have interactions and that delta I starts to pick up a time dependence, then the Hahn echo fails, because if I now look at my delta I, these are now changing at each interval. And so my phase that's accumulated in the first time interval here is not the same as the phase accumulated in the second time interval here. They don't cancel. So you get imperfect refocusing, and this echo decays. And that's a form of what we call spectral diffusion. This flip, often the reason that this is the field is changing is because there are flip-flop interactions among the spins in the bath. Effectively, essentially, this is a spin-bath problem. We have a central spin coupled to a set of bath spins. And so the interactions, the dynamics of the bath cause fluctuations, which cause spectral diffusion. And this is, of course, not refocused by the Hahn echo. And that's what we're essentially looking to measure here. So let's start with the diamond system. Just to remind you, we're looking at system, both the P1 centers and NV centers in diamond. We are doing ensemble measurements. Our experimental system here is a home-built pulsed electron paramagnetic resonance spectrometer at 2.5 gigahertz. The nice thing about this platform is that we can measure NV centers. They have a zero field splitting of about 2.87 gigahertz. And if you there are actually three places at which that transition between the 0 and the -1, two locations at which the 0 and the -1 intersect. One is at 13 millitesla and another one at 190 millitesla. And the P1s have a resonance field at about 89 millitesla here. So this is the P1 line, this is the NV line, and there are two, it crosses the 2.5 gigahertz line, sorry, at two conditions. So we can do EPR at three different conditions on the system. It's a bulk system, so we use a loop gap resonator, the diamond sample on top of it, fiber optic coupled below it. And the fiber optic is used primarily for studying the NV centers. Just to give you a sense of why we do that, this is an experiment, this is a figure of the echo that we detect. In blue, when we don't use a laser excitation, you can barely see the EPR signal. When you shine light to initialize the NV spins, you have a huge growth in the EPR signal. So we are hyperpolarizing the NV centers before we measure them, and we get really nice signals. So this is just, again, if there are anyone's interested in the form of our spectrometer, I'm happy to answer questions later, but this is a home-built system. We use a Quantum Machines OPX system to do all the controls. This is what the echoes look like. So right now what I'm showing you is the time, and the x-axis, you see the time around an echo. So 0 corresponds to what should be the peak of the echo, and the y-axis is the magnetic field. So we're doing a field-swept Hahn echo detection measurement. And the brightness tells you the size of the signal, and the color is indicating the phase. And so here we see for the NV center, we use two diamond samples. One is HPHT diamond, which is high pressure, high temperature diamond. The NV centers are about to 1 part per million or so, it's probably between 4 and 5 parts per million in this sample for the NV center. And we can see that at 193 millitesla, we have a strong resonance peak here, and we have smaller lobes further out. We also have this is exactly the same sample on the top right. This is at 13 millitesla, and you can see the signal once again, and it's spread out a lot more at 13 millitesla. You have different quantization conditions at lower field. This is the same sample, the HPHT sample at 89 millitesla. You see a signal, but it's spread out dramatically, because in this HPHT sample, while the NV centers are around 4 parts per million, the P1 centers are around 50 parts per million. They're actually interacting with each other very, very strongly. So your echo behavior, your echoes are spread out significantly because of the high concentration of P1 centers. We can see a signal barely. However, if we look at a lower concentration P1 sample, so this is a CVD sample, we can see a lot more structure to the P1 centers. And this is where the P1s are also around 1 part per million. And you can see the difference between you have the well-resolved peaks are coming in from the hyperfine interactions, the nitrogen hyperfine interactions of the P1 center, which are much stronger in the P1 than in the NV. All right, so the next experiment that we do is what's called a Karp Purcell Meiboom Gill. It's a dynamical decoupling sequence where essentially we take a Hahn echo like this, and then we keep applying pi pulse so that we periodically just keep generating many, many more echoes. So normally the Hahn echo would be stopping at that first echo here, but we can keep applying pi pulses and generate many, many echoes. And so that's essentially what we do. In this case, we're going to look at the diamond sample. We initialize it with a laser, and then we apply our pi/2 excitation pulse, and then a series of pi pulses, and we watch the echoes decay. So what's interesting here is I want to point out two behaviors. One is that we look at let's start with the 190 millitesla data, which is the bottom two here, the circles, and the squares here. And you can see that as I change the tau spacing from 9.8 microseconds to 13.8 microseconds, which is just the spacing here, there's a little bit of difference between these two decays, but not much else is happening. Okay, these two decays look very, very similar. However, if I'm at 13 millitesla and I use those same two values, this is what I see at 9.8 microseconds. And this is what I see at 13. There's a huge difference. When we ask the question, why does that happen? It turns out that what you're doing is a form of what's called noise spectroscopy. So if you, again, as I'm reproducing the CPMG sequence, so what I would do is a pi over 2 pulse and then a series of pi pulses. My echoes should normally form like this. But if I look at what my spins are doing, or if I look at what a pi pulse does, is it flips the spins by 180 degrees about the XY plane, right? So something that's along Z goes to minus Z at every pi pulse. So you can go into an interaction frame with those pi pulses. So it's called the toggling frame. And that essentially looks like a square wave now. At every pi pulse, I'm flipping the sign by -1. And so you can see that what's shown here is 2 different echo spacings. One is in red, one's in blue. And the toggling looks very different between these two. The blue has a longer period than compared to the red. Now, this B/Z of t is my fluctuating field that I'm seeing along the z-axis. What I actually measure is a product of this BZ of t and this modulation function that I'm producing with my CPMG sequence. And if my modulation ends up being periodic with the signal, I get strong effects. If it's not periodic with the signal, I get a weaker effect. And that's essentially what starts to happen, is that if you're flipping it at a well-defined period with respect at which the spins are already resonant, the flipping the spins has actually no effect, and so your decoherence gets worse or appears to get worse. And so in that sense, you can actually see that the decay of your signal is telling you that you've identified a resonant frequency in the background. So you've characterized the noise of your qubit, if you will. So here's CPMG on NV and P1 centers, and we're looking now at as function of I'm sweeping the value of tau and looking at the time of the echo. So the signals are decaying from bottom to top. So as I go from the time of the echoes very short here in the bottom and then going up to the top, and then I'm changing my tau value, the timing between those pulses, from left to right. And you can see at 13 millitesla, there's a strong oscillation here. And that's entirely due to the carbon-13 Larmor frequency that we see. And so here we're probing this transition at this point here. So the point I'm trying to make here is that we're trying to decouple the spins, but in the process of doing that, we're also able to get information about particular resonant phenomena that are present in the bath as well. So this idea of decoupling is there's no structure to your noise, you get really good decoupling. But if there's structure to the noise, if there are resonant phenomena, you can use the same technique as a form of noise spectroscopy to actually identify what the source of noise is in your system. So this is the figure on the right is a similar experiment on the P1 centers, and you still see this banding that shows up due to the resonances of the carbon-13. This is, of course, now going to be at a much higher frequency because the one on the left is at 13 millitesla. This is at 89 millitesla. So it's, again, much higher Larmor frequency. And by analyzing this data, I'm not going to go into the details, we can actually identify fairly accurately what the resonance frequency is in the two cases. So this is at 89 millitesla, it's just under a megahertz. At 193 millitesla, it's just over 2 megahertz. And here, what we're able to do is really identify do the spectroscopy of these carbon-13 spins, even when our sampling rate, let's say the tau spacing in the echo, is not that is actually cannot be made too short. So you're essentially violating the Nyquist sampling criteria. But by incrementing and looking at all the harmonics, you're able to uniquely identify the signal of the carbon-13 spins. So decoupling is our favorite way in general to suppress the background and quieten the neighbors, except you've got to be careful, because if there's a resonant process in the noise, you can actually amplify the effects of that noise if you decouple periodically with respect to that noise. All right, let's move on to the second experimental platform that I was going to talk to you about, which is donors in silicon. And this, of course, is one of the original platforms proposed for quantum computing. Goes back to the Kane proposal from the late 90s. So you had us where we had donors in silicon being our electronic spin qubits. So as I mentioned earlier, I have my donor electron spin. There's a phosphorus atom right in the middle, and of course the phosphorus nucleus has a phosphorus 31 nucleus spin, and then there's silicon 29, which is typically present in natural abundance at about 5%. The electron phosphorus 31 hyperfine coupling is about 117 megahertz. It's close to isotropic. But then there's many weaker hyperfine interactions with the silicon 29 spins that are anisotropic and spread out across many lattice sites, as I said, because you have a delocalized electron spin. The Bohr radius is on the order of 2 nanometers. Now, phosphorus dopants in silicon are a fantastic system because they've been studied since the 1959. There's a classic paper from Feher where we showed as you change the doping concentration from 10 to the 15 donors per centimeter cubed to 10 to the 16 to 10 to the 17 to 10 to the 18, you actually see a crossover from an insulator, which is with well-resolved peaks here, to the formation of clusters, which is where you see these broad background peaks in the middle, to an impurity band, and a crossover ultimately to a metal insulator transition as you increase the dopant concentration significantly. In fact, this is a system that inspired the idea of Anderson localization. For the SIP data from Feher was really influenced Anderson's thinking about localization. Of course, when we're looking at isolated donors, when we want to look at long coherence times, we want to be in the low concentration regime because we really don't want our donors talking to each other. And so ideally you'd want to be 10 to the 14 or so to make your donors very sparse. So this is a system that's been studied for a long time. There's some wonderful work done from Steve Lyon's group back in the early to mid 2000s, where they took a Hahn echo and they measured the Hahn echo, the spin echo decay of the silicon at different orientations with respect to the magnetic field. So 0 degrees is the 100 direction, is at the magnetic field is aligned along the 100 direction. And 90 degrees is the 011, and of course 54.6 is the 111 direction. And you can see that there's an orientation dependence to the Hahn echo decay. And so at the 100, you have the strongest decay, the weakest decay, so it's the longest coherence times. And as you rotate the crystal, you get stronger and stronger decays. And if you characterize what's called the spectral diffusion time, so the way they analyze this data is you fit this function. There's a component that's due to T2, which is a pure exponential, and then a spectral diffusion time, the component that looks a little bit more Gaussian. N has typically been observed to be around 2.3, 2.4 in most of these spectral diffusion measurements on silicon. And so you have an anisotropy in the spectral diffusion time, and you have a change in this factor N, which goes from about 2.3 or so at most orientations to almost half in the 100 orientation. And this is primarily due to interactions with silicon 29. So there was some beautiful theory that was done to study this. There's the work from both the Renbal Liu's group and Witzel and Dasarma, where they actually then came up with an analytical theory, at least to explain the angular dependence of the decays. And you can see that the echo intensity, and just showing you the final result, depends only on the hyperfine interactions. AI and AJ are the hyperfine interactions with spins I and J, nuclear spins I and J. Dij is the dipolar coupling, but nuclear dipolar coupling between spins I and J. And so these echoes should depend only on the hyperfine couplings and the internuclear dipolar couplings and nothing else. And that's what these decays show. And there's a beautiful agreement between theory and experiment from these low field measurements. So these measurements were done at X band, which is a standard, which is about around 9 gigahertz for the electron spin resonance, which is about 0.3 Tesla in terms of magnetic field. And there's really some beautiful data and lovely theory that showed that that explained the data really well. So this is really, again, this is a spin bath problem. Your Hahn echo actually in some ways is telling you about how the central spin is getting entangled with a bath. And in fact, it can be a measure of the entanglement entropy. In this case, at low field, it's hard because you can't provably show that you have sufficient, that neither system is in a pure enough state. But if you go to high field, you know that the central spin is definitely in a pure state. And so you can map onto a model of entanglement entropy here. So what's the first thing that people did when they're trying to build silicon qubits is, let's get rid of the silicon. And so this is the echo intensities this is from Koei Ito's group, where they did some beautiful work on isotopically engineered silicon. And they changed the isotope concentration of silicon. So 5% is a natural abundance, but they grew silicon crystals with very, very low concentrations of silicon-29. And you saw that, and you can see that the timescales extend up to 10 milliseconds essentially. And also 100% silicon-29, in which case they shortened all the way down to 10 microseconds. So there's a 3 orders of magnitude in difference in the spectral diffusion times based on the concentration of silicon in the system. So this was really, really impressive data. And of course, it tells you that what you have to do to extend coherence times of these phosphorus donors in silicon is to suppress the silicon-29 spins. And of course, the simplest way to do that is just get rid of them all entirely. So which is what, if you can isotopically grow silicon crystals which have no silicon-29, you have very long coherence time. So all of the really fantastic work coming out of Australia and the Andrea Morello's group is all done on silicon-28 substrates. That's the first thing that you do, is you get rid of all the silicon-29 in the crystal. And you have that essentially suppresses the dominant source of dephasing for most phosphorus dopants. Of course, at that point, you start to worry about other mechanisms start to become important. But at least you've now got this huge improvement in coherence lifetimes from the order of several hundred microseconds all the way to 10 milliseconds. So what we did was we actually went to high fields, and we're now doing some experiments at 8.58 Tesla, which is 240 gigahertz. And we took just natural abundant silicon, and we wanted to study just their coherence properties, because not a lot has been done at high magnetic field. And there also some interesting behavior that's been observed at high magnetic fields with optical excitation, because you can start to hyperpolarize the phosphorus donors in these experiments. So we went to high magnetic field and 240 gigahertz. And what we saw first in the dark was, this is the decay in red, that it had a fairly short coherence time. The dashed green line, or dashed yellowish green line, is what you have is what the theory predicts that I showed you earlier. That the theory that gave us beautiful agreement with the experimental data at low magnetic field disagrees pretty dramatically with the data at high magnetic field. But if you looked at the theory, the decay should depend only on hyperfine couplings and nuclear dipolar couplings, neither of which should be field dependent. So it's really surprising that these decays are much shorter. And then the other surprising thing we found is that when we shone light on it, so we took 1051 nanometer IR excitation, our coherence times actually increased. So normally when you think of shining light on a sample, you're creating carriers, you're creating thermal electrons, you're creating a noisy environment. In almost all experiments, when you shine light on something, unless you hyperpolarize the spins, you essentially shorten your decoherence times. Whereas here, we're actually increasing the coherence times. We're quieting our neighbors by shining light on, which is surprising. Just to make sure it was a light that did it, we swept the wavelength of the light. This is from off, and then we went from 1090 nanometers down to 1050. The silicon band gap at 4 Kelvin is about 1060 nanometers, and we see that this effect, the spectrum, starts to show up right around there. So really, what it requires is above band gap excitation of above band gap optical excitation is what is causing this change in coherence times or spectral diffusion time from 110 microseconds to about 185 microseconds. There is a variation also in the value of n, the stretch factor, going from about 2.2, which is what we saw at low field as well. But so we see a similar factor at high field in at long wavelengths, but at the shorter wavelength, it starts to shorten a little bit. So this is something we did not expect at all, and we do not understand at all. And I'm not sure we completely understand it yet. So just to be careful, what we did was we said, well, we know that if you turn up and we make the power large enough, T1 and T2 have to get shorter, because that's just, you're putting in thermally polarized carriers, things have to get short. But what is happening at intermediate scales? So we did this measurement as a function of power. So this is now on the x-axis is the power of the lasers, and the y-axis we're measuring either the spectral diffusion time. We're doing both. We're measuring the spectral diffusion time and the T1 or spin lattice acceleration time of the carriers, of the donors. So the T1s are very systematic. You see that they start at about 10 milliseconds, and then they're flat for a while. They don't change a lot. And then at some power levels around minus 20 dBm, they start to slowly get shorter and shorter, and then it crashes down. But if you look, and that's true at both orientations, the 100 and the 111. If you look at the spectral diffusion times, for the 100, we don't see much of an effect. It stays pretty flat with respect to light. And then maybe there's a little bit of an increase here, but it's very noisy. And then everything decreases with the T1 of light, the T1 shortening T1 due to the presence of light. But at the 111 orientation, you see that there's actually an increase in the spectral diffusion time. And that's exactly what we saw earlier, but it's only present at low optical powers. If you turn up the optical power, you can actually see the effect of shortened T1. And it's a shortening T1 that basically shortens everything out. We've done this experiment with both, this is 1040 nanometer excitation. We've done it at 980 nanometer excitation and 1047 nanometer excitation. So this is what's shown on the bottom right. And we can do it on the low field or the high field transitions of the EPR line, and the behaviors are all pretty much identical. So it seems to be a general phenomena that is not that sensitive to the wavelength of the light. It just needs to be near band gap at this point. What we do have a hint of is that the effect is weakest along 100, and that is and the orientation dependence of the spectral diffusion time is primarily due to hyperfine interactions. So this suggests that at high magnetic fields, where somehow the hyperfine interactions are modified, and you're getting an additional anisotropy due to the hyperfine interactions. So we then also looked at the variation of the spectral diffusion time with respect to the angle, and we see that's in the dark with the laser off. You get this is what we observe. It goes from about 450 microseconds to about 120 microseconds. So it's almost a factor of 3. And in terms of the anisotropy, and then it changes when you turn the light on. It's down to a factor of about 2.5. Just to compare, I've shown the X-band 0.35 Tesla data on the right. Here, the anisotropy is only a factor of 2, so it goes from about 600 microseconds down to about 300 microseconds. So there's a factor of 2 anisotropy in the spectral diffusion times, whereas here in a high field we have a factor of 3. So the anisotropy is higher also at higher fields, which again suggests that somehow the high field conditions are essentially perturbing the wave functions of the donors in silicon and giving us modified hyperfine interactions, which again, the presence of light is then causing some sort of emotional averaging or additional perturbation of those wave functions, and shortening and reducing the size of the hyperfine interaction and increasing the coherence times or the spectral diffusion times. That's our model, at least right now. But this is data that we've collected over the last few years. We don't have a great theory for it. The challenge with doing things like CPMG, which are noise spectroscopy at high field is that your phase stability of the 240 gigahertz source is limited. So you can only do about 3 pulses with reasonable phase coherence. So some of the techniques that we would normally use at low frequencies can't be used when you go to these high field conditions. All right, we're coming towards the end of time. I want to have time for questions. So the key message that I want to you convey is that understanding the local physics of the spins is critical to identifying the limits to decoherence and potentially controlling them. Depending on your physical system, there are different techniques that can be used to essentially extend coherence times and suppress the presence of a spin bath. But not all of them, and all of them will work on only a restricted set of criteria of conditions. So in Diamond, we saw that dynamical decoupling allows us to both suppress unwanted interactions, but of course, we also remain sensitive to desired interactions up to a point. That's assuming we actually want to measure the carbon-13. Sometimes we may not want to measure the carbon-13. We might want to measure, if I'm using the Diamond as a sensor, I might want to measure protons, or I might want to measure some other signal if I'm using this as a magnetometer. So I want to preserve sensitivity to that signal. But in order to do that, I need to make sure that typically I can only do AC sensing. It's almost impossible to do DC sensing with Diamond, unless you actually do things like spin the diamond, which is something that's recently been done by a couple of groups, where you actually spin the diamond, and that reintroduces sensitivity to static fields. In natural abundant silicon, we're actually seeing that we can suppress spectral diffusion by turning light on, and we're curious to see if this effect persists at low field, because then an alternative to isotopic engineering could just be using optical engineering to extend coherence times in phosphostope silicon. All right, thank you for your attention. And again, I'm going to put up my acknowledgements at the end. I'll take questions.
Thank you very much. Any questions for us?
Could I maybe ask?
Okay, Forrest, then answer. Forrest, go ahead.
Thanks for the nice talk. Could you maybe sort of, in layman terms, indicate what the outlook is now for, say, the field of quantum sensing? With your results, what will be able to be done now?
So with quantum sensing, I think with quantum sensing, I think the NV center in Diamond is a really good sensor, and the work that's been done recently on building Diamond cantilevers and building you can now put Diamond into a scanning and design a scanning microscopy system with nitrogen vacancy centers. So that's now, there are several set of companies have been formed. It's becoming a really important tool to look at surface physics of materials as just a characterization platform. It's because it can be used at room temperature. It's really useful for things like ex vivo measurements. If I look at biological samples as well, you can study cells and you can study flow. In vivo, of course, it's a lot harder if you want to actually get into and start to do sensing in inside a body or inside a biological system. I think there you still have significant challenge to do things like far field measurements. But I think near field measurements, I think there's a lot of potential in terms of how the key feature is, how do you get your NV center close to what it is that you want to study and suppress and get high enough quality diamond that what you're seeing is this material outside the diamond and not strain or other stress factors inside the diamond, if you will. But I think there's a lot of growth in engineering diamond structures, engineering how you can implant defects in diamond, and how well you can control those the spins in diamond so that you can focus on what information you want to get out of the system. I hope that answers your question.
See, thanks. Yeah, I was wondering, like, specifically the results you presented.
Yeah.
What do you envision? Do they move the field somewhere where we haven't been able to go before? Or?
So the diamond question, I think the key result from ours is that the nature of so right now, a lot of what's been happening with diamond is With single NV detection, people will take a diamond sample, HPHT, or which is high pressure, high temperature, or CVD diamond, and they'll hunt around for a good for a good NV center. And a lot of that is trial and error. You find out something that works well, and because you have inhomogeneities in how the diamond is made, it's not clear that you can get reproducible diamond quality. And then you find a good center and you do your experiments on that center. There is some recent, and the challenge with what we're showing here is how methods in which you can characterize the quality of diamond. What is the nature of the background noise processes within diamond, and can you control some of them, while which of those are controllable and which of those are not controllable from a materials growth perspective? And that's a question we're trying to discriminate between. So for example, if it's just P1 centers in the NV that are the noise source, if I'm just doing nitrogen implantation, I could get rid of a lot of the P1 centers as my noise and primarily look at other defects as being the source of noise. Often though, the coherence time of some of those implanted defects is not always as good as naturally grown defects. So there's a tension here between how do I engineer the right diamond structure that has the longest coherence times? The longest coherence times are still ones that are grown with things like either natural diamond or CVD diamond, which are very clean. But there it's harder to control exactly where the diamond is. Ion implantation helps you determine where the diamond is, but you also end up damaging the lattice a little bit, and you have other challenges with the quality of the coherence times. So I guess the question, the point I'm making is that you're in an in-between. We're still in the process of trying to figure out how do we get the best of both worlds. Really long coherence times while we have well-controlled positioning for diamond. So that's from the sensing perspective, I would say that's our most important question. From the part that I'm personally actually more interested in is studying many-body physics of the P1 centers. And there, knowing what the nature of the P1 centers is, the nature of the clustering of P1 centers and those interactions is really important to determine to think about the types of physics questions I can ask. Are they strongly interacting? Are they weakly interacting compared to the disorder? Am I going to see signatures of phenomena like many-body localization? If I want to look at dynamics such as hydrodynamics or transitions from non-hydrodynamical behavior to hydrodynamical behavior, I don't want to infer some of that behavior just from the data. I want to actually get a little bit of information about what is the ordering or the structure of the bath before I infer some features of the baths.
I see. Thanks.
Yeah.
Yes, thank you, Shekhar, for this wonderful talk. I have several questions, but I think I would only ask a few of them in the interest of time. The first and obvious is from DLP point of view. So do you think something similar might be happening in a DLP setup where upon microwave irradiation, because of nuclear alignment or hyperpolarization, the T2 is getting longer in real time?
So that's a possibility. The suggestions are from those early work from Daniel Loss, when you're looking at quantum dot systems, they suggested that the nuclear spin polarization had to be over 90% to really extend the coherence times. And for phosphorus donors in silicon, at least Susumu, Takahashi had shown, and David Ashlam showed that actually under exactly in the same system that we use here, 240 gigahertz and 4 Kelvin, they got very long coherence times of NV centers in diamond by hyperpolarizing the P1 centers. And so, but then they were also in a regime which was over 90% polarization. Can you see features where extended coherence times where the hyperpolarization is not that high? Is something I don't know yet, if that's the case. Because even in our experiments, I don't think the phosphorus donors are actually getting hyperpolarized. I mean, I don't think the silicon is getting hyperpolarized because the time scales are very short. I can turn the light off, and when I turn the light off, the T2 goes back immediately to the value that we see in the dark if I rerun the experiment. Whereas if the silicon was getting hyperpolarized, the silicon T1s are several hours. Even at room temperature, the silicon T1 is up to 4 hours. So at low temperature, it's almost a day. And so when you hyperpolarize these things, that the effect should stay for a really long time. And so we're pretty sure that it's not hyperpolarization. Also, there was some work from Yoshi Yamamoto's group in the 2000s again, where they studied optical hyperpolarization of silicon-29 nuclei, and they had to turn up the power levels and into the realm of several hundred milliwatts to see hyperpolarization. And for us by that time, we're seeing our coherence times have essentially gone shortened dramatically.
Okay. And yeah, I will think more about it and I'll get back to you through email on that. Regarding this longer coherence time, so right now you're not doing anything on nuclear spins. You could be doing RF radiation, and that, I suppose, would make it
Absolutely.
longer.
Yeah. So I think definitely you could do decouple in both systems. I think in the electron spin system, you could, if I did something like what's called a Lee Goldberg decoupling of the P1 systems, that should dramatically extend the NV coherence times. And similarly for the phosphorus doped silicon system, if you did that on the silicon spins, double frequency radiation, that should dramatically extend the coherence times as well by suppressing the flip-flop interactions between the bat spins.
And how does the spin diffusion barrier affect T2? Like compared to, say, phosphorus, where you said the electron spin density is over a wider range. So is spin diffusion barrier more stringent compared to NV center?
So there's a difference. The spin diffusion barrier plays a role. Again, this question of how real of a barrier is a different question. A lot depends on time scale. So if we think about most strongly hyperfine coupled silicon spins, they're about 4 megahertz shifted from the central line. And so at that point, a flip-flop interaction between nuclear spins is going to be suppressed because the nuclear spin Lamer frequency here is about 79 megahertz. And so 4 gigahertz shift is significant. And you're not a nuclear dipolar couplings on the order of tens of kilohertz. Oh, actually here, it's less than that, on the order of several hundred hertz. It's less than a kilohertz. And so you're unable to, you essentially don't have thermal contact between the strongest hyperfine coupled spins and the bulk spin bat, the nuclear spin bat. So those spins that are within the nearest hyperfine coupled shells are typically almost like a frozen core. They don't change. They're not undergoing flip-flop. They provide a fixed field. It's the more weakly hyperfine coupled spins that are where the hyperfine coupling is comparable to the dipolar coupling, that are able to undergo flip-flops and give rise to a fluctuating field. And it's that fluctuating field that's limiting the T2. Because a fixed field really just provides a shift. It doesn't really do anything. And those spins are going to get refocused by the Hahn echo.
Yes. So in the case of NV versus phosphorus center, in which case your barrier would be larger? Because you mentioned in the other case, the latter case, the electron density is more spread out.
Yes. So it turns out that the barrier is. So the barrier, and I'm sort of the reason I'm humming and hawing is that they're slightly different situations. The hyperfine couplings are very different, and the experimental conditions for these two experiments are different. So the hyperfine couplings, for example, in silicon are only about 5 megahertz, whereas the strongest hyperfine couplings for carbon can be up to 100 megahertz. And often you can be, for the near spins in diamond, you can be in regimes where, or actually, for the nitrogen, it's it's on the order of 100 megahertz. For certain carbon, it's also, I think, very high. So you need to go to, and most NV experiments are done at very low field. And so you can be in a significant region where the hyperfine couplings dominate the Zeeman interactions for a long time. This is why if you look at Tamiyao's work from Delft, they can resolve 30 to 40, over 30 nucleus spins, and they're developing 30 qubit systems based on NV centers and diamond, because you can get these strong hyperfine resolved peaks that are separated from the bath. You can't do that with silicon. And I think that's just the nature of the hyperfine coupling and the different anisotropies that you have.
Okay. I have a question regarding slide number 23. So you showed one equation for the fluctuation.
Okay, I'm gonna have to, let's see if I can go back. So,
I think it was slide number 23.
there you go.
Yes, so in this echo intensity,
Yeah.
square difference of hyperfine coupling.
Yeah.
That is coming because one wants to minimize the flip-flop interaction.
So, maybe the easiest thing for me to show you is actually to send you the calculation for it. It's what ends up being really is you can do this from a spin bath calculation, where and the key feature here is this is called what's a pair correlation approximation, which says that I only need to worry about flip-flop interactions between two nucleus spins at a time. And so when I look at a pair of nucleus spins, what determines the rate at which they flip-flop is a difference in resonance frequency, which is a difference in the hyperfine interaction, and the dipolar coupling. And that's why those are the two factors that come into it. And then you take a product of all such pairs present in the system. But that's an approximation that works for the Hahn echo. There are also it's part of a cluster approximation approach to studying many-body physics. So this is the first order expansion of a multi-point expansion, really. So it's the simplest approximation, but it turns out to give very, very good agreement to the Hahn echo.
Okay.
And so here what you're doing is you're taking just one pair of spins at a time and saying, okay, what's the likelihood that they'll flip-flop? And that's going to depend on what their relative hyperfine interactions are, as well as their dipolar couplings.
This is more valid at low magnetic field, right?
So this is this does assume that you have it's derived under an approximation of an unpolarized nucleus spin bath, so that you essentially that the nucleus spin bath is essentially in the identity state or very high temperature state.
Okay. I have the final thing.
Yeah.
And then have a Zoom meeting later on. So we are also making an energy sensor, and I saw in your initial setup we are using quantum machine.
Yeah.
So what's your experience with that? Is it like a pulse blaster for you?
So we have two systems. One is based on a pulse blaster and an AWG, and the second is based on quantum machines. You can build everything that the quantum machine does, probably with little light, less money. The advantage of quantum machines is that they've made it easier to program. So if I want to change the pulse program and things like that, it's easier for us to make those changes and upgrade the experiments quickly with the quantum machines, because again they provided a Python-based programming environment, which is what they call a QA package is what they have, and it has bugs and it has some features to it. It's not perfect, but the turnaround time and the ability to train people is faster. That's the main distinction. You can probably build a slightly better featured system, but the challenge often is the software that you have to write. And each time you change the software or change something, there's a lot more programming that has to happen. And I think it's from that perspective that quantum machines often ends up being a little easier. You can bring people up to speed faster, and you can and you can design new experiments. You can write new experiments faster.
So, yeah, does it need to be compatible with the microwave source? With other?
No, I mean, we use a standard microwave source and our own microwave source. It just provides, you just use it to control the mixers, that's all. I can, again, I'm happy to chat with you offline if you want to get more details.
Sure, thank
Yeah.
you.
Okay, any other questions? Okay, if not, let's thank Shekhar again for the very nice talk. Thank you very much.
Thank you.